Hey students, we're going to go over waves and light and how the electron is involved in all of this. So we'll start here. Let me move my little picture. All right, so this up here is a Bohr model. This is what we're familiar with from middle school. We know from our last unit that the protons and the neutrons are found inside the nucleus here in the center. That's why this has a positive charge, because protons are positive. We know that the electrons are found out here in the electron cloud. Now you may remember from middle school that when you draw these Bohr models, these rings around the nucleus represent energy levels, and there's lots of different energy levels surrounding the nucleus here. So can electrons be found in any energy level? Yes, they can. It depends on how many electrons you have, on which energy levels they're going to be found in, and then it also corresponds to how much energy these electrons have. So let's think about this. Do the electrons want to be closer to the nucleus or further from the nucleus? So we're going to think about Paula Abdul's hit song, Opposites Attract. Okay, opposites attract. The nucleus is positive, like we were talking about, and the electrons are negative. So the closer they are to that nucleus, the stronger the attraction. So if they're very close to the nucleus, it doesn't take a lot of energy for the electrons to stay there because the attraction is holding them close to the nucleus. But if you move further from the nucleus, the attraction gets weaker because there's more distance separating those positive protons and the negative electrons. And so they need more energy associated with the electron if they're farther from the nucleus, because the attraction is weaker. They need more energy to hold themselves around the atom itself. Okay, that's going to be an important point in this lesson. So we call this the ground state and the excited state. Now this represents carbon atoms. Okay, each of these is a carbon atom because there's 6 protons in the nucleus here. Now this first energy level can only hold 2 electrons, and we'll get to talking about how to draw Bohr models here on another day. And the other 4 electrons are found in the second energy level. This first picture here is called ground state because it doesn't take that much energy for those electrons to be there. That's as close to the nucleus as they can get, because we can't have more than 2 in that first energy level. So this has the lowest amount of energy for these electrons right here. Now, while you're in ground state, those electrons can take in energy. You can see in the picture here that we have energy going into the atom, and that energy excites the electrons, and when the electrons get excited because they have more energy, they're able to move further away from the nucleus, like in this second picture here. You can see that this electron has jumped to a higher energy level. It's now in the third energy level. This is what we call an excited state because the electrons have a lot of energy that they just took in. Now these electrons, they don't stay in an excited state. They can't. It's too much energy. They're going to give off this energy so they can get back to where they're comfortable, back to ground state. So you can see in the last picture here, this little blue wiggly arrow leaving the atom, that's energy being given off. And the electron can return back to what we call the ground state, the lowest energy state. Now, this energy that's being given off, that's being given off in the form of light. And some light we can see and some light we can't. But the energy travels in waves, and those waves correspond to different colors of light or different types of energy that we can either see or we can't see. All right, so ground state, lowest energy state. As close to the nucleus as they can get. Excited state, they've got more energy, they've moved away from the nucleus, but they can't stay there. They're going to give off that energy, and they're going to come back to ground state. Now, I'm going to stop sharing this for a second, and I'm going to move to showing you a little simulation. Let me go to my, okay, here we go. So you can see here, we've got a little simulation. We've got an electron down here on solid line, which is the ground state, and then these dashed lines represent excited state. So these dashed lines are different energy levels. And you can see that we have different amounts of energy over here that we can give the electron. And the electron needs a certain amount of energy in order to go up to a higher energy state. Well, what happens if we give that electron some energy? We put some energy over here. Let's excite that electron. It jumps up to a higher energy state, but it doesn't stay there. Notice this graph down here, as the energy returns, or as the electron, excuse me, returns to ground state, it gave off energy, and energy travels in a wave. So that's why we see this graph down here, okay? Now, if we give it a little bit more energy and excite it again, now we've given it so much energy, it can jump up to a higher energy state. As it comes back down, it's giving off a different amount of energy. That's going to correspond to a different kind of thing that we can either see, okay? We have a shorter wave here, and we're going to talk about this in a little bit here. We can give it even more energy this time, and we can excite it so much that it jumps up to an even higher energy level. But again, notice the wave of energy that is giving off down here. I'm going to go back to our PowerPoint so we can continue. Okay, so let's check for understanding. A hydrogen electron makes a transition from n equals 3 to n equals 1. N is going to represent an energy level. So it's going from energy level 3 to energy level 1. Which of the following statements is correct? Well, remember, a higher energy level means that we're getting further from the nucleus, so there has to be more energy associated with a higher energy level. So if you're going from n equals 3 to n equals 1, that means that the electron is going to have to lose energy to go back closer to the nucleus. So we know that number 3 is true. The electron has to lose energy. Well, the reason why it loses energy is because of number 1. Energy is emitted. It's given off energy. So 1 and 3 are true. Let's look at this one. The light produced by signs using neon gas results from electrons that are, okay, so light. Light is a form of energy. Light that we see means that energy has to be given off. The electrons have to be releasing this energy as they return to ground state. So letter A is going to be our answer, moving from a higher energy to a lower energy, because if it's going from high to low, it has to give off and release that extra energy. Letter B, moving from a lower to a higher, if you're down here and you need to get up here, it needs to absorb energy to go up to a higher energy level. And letter C and D, electrons being lost and gained, that takes into account bonding, and we're not there yet. Okay, we haven't talked about that, so it has to be letter A. Now, these energies that are being given off by the electrons, they correspond to different wavelengths of energy and different wavelengths of light that we can see. And we can look through a diffraction grating and see these different colors of light being given off by these different atoms. And you can see here, this is a hydrogen emission spectra. This is what we would see if we looked through a diffraction grating at hydrogen, these different wavelengths of light. Those are the only wavelengths and energy of light that the hydrogen electrons can absorb and then give off, okay? Each element gives off a different emission spectra. So we have different kinds of spectra, line spectra. We have a line absorption spectra, and we have a line emission spectra. So think about what absorption and emission mean. A line absorption spectra is showing the wavelengths of light that the atom is absorbing. So all these black spaces here in this top picture represent the wavelengths of light that the carbon atom is absorbing, it's taking in. Whereas the emission spectra, emission means to give off, emit, give off. So those colors down here correspond with the wavelengths of light that the electron is giving off. And notice that these are opposite. Whatever the energy of light the atom is taking in has to be the same as the energy of light it's releasing and giving off, okay? So which element is represented in the line emission spectra? We have absorption spectras to choose from. So we're looking to see which of these absorption spectras correspond to this emission spectra up here. Well, we can automatically eliminate mercury because mercury has all of these colors in the green and yellow area that this unknown doesn't have. So now we're between sodium and lithium. And I can see that sodium is going to absorb some wavelengths of light in the yellow and orange that are not present in this emission spectra for the unknown. So I can see that it's going to have to be lithium because the missing pieces of the line absorption for lithium are showing up in this emission spectra for the unknown. So again, let's do some checks for understanding. Now, the following transitions in the Bohr hydrogen atom, the blank transition results in the emission of the highest energy photons. So first off, remember N is our energy levels. So it's talking about the emission of the highest energy. Emission means giving off. So let's think about this. Are the electrons giving off energy when they go from a low to a high energy, or when they go from a high to a low? Well, they're giving off emitting energy when they go from high to low. So we can automatically eliminate answer choices B, C, and E, because those ones show that it's absorbing energy. So that means it has to be A or D. So we're looking for the one that has the biggest transition. And letter A is going to have the biggest transition because it's going from energy level 6. The electron is all the way up here. It's going all the way down to energy level 1. Okay, so that's going to give off the highest energy photon, particle of light. Then the next question, the lines in the emission spectra of hydrogen result from A, electrons given off by hydrogen as it cools. Well, the electrons being given off, that's not happening yet. That happens with bonding. We're not talking about the electrons given off. We're talking about the electrons giving off or releasing energy. B, decomposing hydrogen atoms. We know that's not the case. C, electrons given off by hydrogen when it burns. Again, the electrons aren't being given off. They're releasing or absorbing energy. D, energy given off in the form of visible light when an electron moves from a higher energy state to a lower energy state. Well, that sounds pretty darn good, because we know that emission means to give off. So it says energy is given off. We know that's true. And it has to be from the high state to the low state in order for it to give off and release energy. And then E, protons, we can see that word and automatically eliminate it because we're not talking about the proton here. Proton's not doing anything. So we're going to look at this wave here because energy is traveling as a wave. So we're going to label different parts of the wave. First off, wavelength. When you label a wavelength, you want to go to the same corresponding parts of your wave. So here, we've got it labeled from the top of one to the top of the next. You can label it from the bottom of one to the bottom of the next. You can label it from the start or the origin of one to the origin of the next one, as long as you're going from the same point on the waves, okay? The peak or the crest, I use both terms, is the top of the wave. The bottom of the wave is the trough. And then we have amplitude. So amplitude, notice, is going from the midpoint to the peak or from the midpoint to the trough. It's not all the way from the top all the way to the bottom. It's from the midpoint to the top or the midpoint to the bottom. Okay, so I'm going to take a look at this simulation. So I have to stop sharing, and I'm going to share my other screen now. So I'm going to go here to this PhET simulation. Now I'm going to go ahead and start. I have this as oscillate, so it goes automatically and I don't have to manually make the wave go. And I'm going to make it no end here. All right, so you can see here that our wave is moving down this line out the window or whatever that is. A couple of things. Amplitude, again, amplitude is the height of the wave from the midpoint up to the top or the midpoint to the bottom. Frequency is defined as how many waves pass through a point at a given time. It's not the same thing as speed. Frequency is how many waves pass through the point at a given time. All right, so you can see as the wave goes, we can increase our frequency, which means more waves are going to pass through that point. We can decrease the frequency, which means less waves pass through that point. Okay, what I want to do is show this relationship between wavelength, frequency, and energy. So this is going to be our standard here. Okay, now here I'm going to pause it again. Wavelength from the top of one to the top of the next. I don't have a bottom here to show you the bottom, but the wavelength, I want you to see what this wavelength is compared to when I stop it on a slower frequency or a higher frequency. Notice the amount of energy associated with this wave. Okay, what happens when I decrease the frequency, make the frequency lower. What's happening to the energy of that wave? Well, we can see visually that the energy of the wave is going down. So the lower frequency makes lower energy wave. And look at this wavelength. The wavelength, did it get shorter or did it get longer? Well, I can't even get a full wave in this picture here. So the wavelength got longer. So when we have a low frequency, we have low energy and we have a long wavelength. Now what happens if I ramp up this frequency? Look at that energy. What's happening to that energy here? Well, the energy of the wave is increasing. When we have a high frequency, we have a high energy. There's lots of energy associated with this wave. Let me pause it. Let's look at our wavelengths. Now I've got lots of different wavelengths here. So my wavelength got shorter. So when I'm at that high frequency and high energy, I have a short wavelength. So if you want to, you can click on that picture in the PowerPoint and play around with that a little bit. So there's different types of radiation and light that the waves can give off, and not all of the light is in the giving off wavelengths that we can see. Okay, so electromagnetic radiation is any kind of energy that gives off this wave-like behavior. Okay, so this is called our electromagnetic spectrum. So notice it composes of radio TV waves, microwaves, infrared. The visible light spectrum fits right here in the middle between infrared and ultraviolet. Okay, we have ultraviolet, X-rays, and gamma rays. Now the part here on the left, this is my low, long side. Let me go ahead and label this. Okay, I like to call this side my low, long side. That is my low energy, it's my low frequency, it's my long wavelength, okay? This side over here is my high, short side. This is my high energy, it's my high frequency, it's my short wavelength, like we saw in that simulation we just did. Okay, so the low, long, high, short. If you look at your visible light colors down here at the bottom, you can see that red colors are associated with a lower energy, a longer wavelength, whereas your violet colors are associated with a higher energy, a shorter wavelength. Okay. I want you to think about it in terms of the radiation that you've personally come in contact with. We've all listened to the radio. We've all watched TV. We've all used our microwaves. Do we need any kind of personal protection for ourselves when we're listening to the radio or watching TV or cooking our food in the microwave? No, we don't. Okay, and that's because those forms of radiation are at such a low energy. We don't need any kind of protection, but think about this stuff on the other end. Have you had an x-ray before? What kind of precautions do they take when you have an x-ray? Yeah, they put that vest on you to protect anything that's not being x-rayed itself. The technician goes into another room and hides behind a curtain, okay? What about those of you that have used tanning beds before? They make you wear those little goggles over your eyes to protect your eyes from that ultraviolet radiation. That's because ultraviolet light in x-rays are your higher forms of energy, so we need to protect ourselves against those higher forms of energy. So what we want to make sure we do is memorize this order, okay? From the low, long side to the high, short side, and where those colors fit in here. Don't forget about this visible light spectrum fitting in right here in the middle. So we have a little saying to help us to remember the order. It's red Martians invade Venus using X-ray guns. It corresponds to the different parts of the electromagnetic spectrum. Red Martians invade Venus using X-ray guns. Radio, TV, microwave, infrared, visible, don't forget your visible light, fitting in between infrared and ultraviolet, then ultraviolet, X-rays, and gamma rays. Make sure you know this order so that you can quickly answer questions about that, okay? We're gonna stop this one and we're going to do wave calculations in another video. So let me know if you guys have any questions.